Hey everyone, and welcome to this explainer. Today, we're unpacking a massive leap forward in oil and gas technology. We're going to trace the really fascinating journey of well data architectures, moving from traditional data storage methods all the way to modern, high-speed, real-time streaming right out there on the rig. If you work with well data, you know that timing is literally everything. And the protocols we're diving into today are exactly what make right-time decisions possible. So let me ask you a critical question. Is your drilling data arriving too late? I mean, really look at your current data architecture. Are you suffering from network latency during those crucial, time-sensitive drilling operations? Are polling delays keeping you from seeing what's happening at the drill bit the exact second it occurs? Well, in this explainer, we're going to figure out exactly why that happens and, more importantly, how the industry has evolved to completely fix it. Okay, let's dive into this. Here is our roadmap for today. First, understanding Witsml. Second, the traditional store API. Third, the need for speed. Fourth, streaming with ETP. And finally, number 5, real-world data flow. Section 1. Understanding Witsml, the foundation of well data. We really can't build a high-speed highway without first understanding the roads that are already paved, right? And that baseline, that paved road, is WITSML. That stands for Well Site Information Transfer Standard Markup Language. At its core, it's a set of XML data object definitions and a web services specification. It was developed to promote the seamless flow of well data between operators and service companies, to speed up and enhance decision-making. You can kind of think of it as the ultimate common language for drilling. It provides the essential schemas for pretty much every object you can think of: wells, wellbores, tubulars, and, of course, your logs. Picture the basic setup here. You've got a Witsml-enabled client application on one side and a Witsml server on the other. The client sends requests, specifically XML query documents, over to the server using SOAP protocols. The server then takes those, validates the documents against Witsml XSD schemas to ensure everything is perfect, and then sends a response back. It's highly structured, it's very reliable, but as we'll see in a minute, it requires a whole lot of back-and-forth communication. Section 2. The traditional store API and polling for data. Let's explore how this data has historically been requested and stored. Within the traditional Witsml store API, the client and the server have very distinct roles. The Witsml client is the active participant here. It initiates the requests, it queries for data, and it pushes the XML documents. The Witsml server, on the other hand, is essentially passive. It simply exposes specific SOAP functions, validates the incoming schemas, and either stores or returns the data objects just as the client requested. The server never just hands over data on its own, it always waits to be asked. So what do those interactions actually look like in practice? Well, a client executes a very specific step-by-step sequence of SOAP functions. First up, it calls WMLS_getVersion to check which versions of Witsml the server actually supports. Second, it calls WMLS_getCap to determine the server-specific capabilities. Third, if it wants to push data, say a new log, it uses WMLS_add_to_store. And fourth, if it wants to pull data down, it uses WMLS_getFromStore. It's a very deliberate conversational handshake between the software components. Let's anchor this in a real-life illustration. Imagine a sensor aggregator application on the rig acting as the client. It collects real-time sensor data, packages it all up into a log data object, and pushes it via an HTTP post, using that WMLS_add_to_store function straight to the proprietary data store on the Office server. Then, the Office applications can use WMLS_getFromStore to pull that data down. It works beautifully for static data, but what about real-time, rapidly updating data? Which brings us to Section 3, the need for speed, and why polling just isn't enough. This is where we really find the friction point. Modern rigs generate massive amounts of data every single second, and the traditional API honestly starts to show its age under that kind of pressure. But seriously, what happens when data needs to flow instantly? Using the traditional API for real-time data is literally like a kid in the backseat constantly asking, "Are we there yet? Are we there yet?" That is polling. What you actually want is a live GPS feed. So the crucial point is that traditional polling has some major limitations for live drilling logs. It relies on really heavy XML payloads. We're talking lots of text and markup just to send a few numbers over. It forces clients to constantly bombard the server with WMLS_getFromStore requests just to see if new data arrived. All those repeated queries generate a ton of excessive network traffic, and ultimately, that creates very noticeable latency for systematically growing logs. And when you're making split-second decisions at the rig, latency is the absolute enemy. Section 4, Streaming with ETP, the Energistics Transfer Protocol. The industry totally recognized this bottleneck, and here is the ultimate solution.
ETP, the Energistics Transfer Protocol, is a completely new specification built for true data streaming. The game changer here? Receivers no longer poll. Providers push the data instantly, cutting latency to near zero. It's so wildly efficient that it's even been adapted to replace legacy SOAP APIs in older Witsml versions.
ETP pulls off this incredible speed by abandoning heavy XML markup and going with JSON instead, JavaScript object notation. By stripping out all those heavy, clunky tags that XML requires, ETP creates a tiny, hyper-efficient payload that can just fly across rig networks without clogging up your bandwidth. So the crucial point is how we actually establish this stream. ETP uses a set of specific protocols to make it happen. To stream log data, you rely primarily on two stable ones. Protocol 0 is the core protocol. Its entire job is to create and manage the overarching ETP sessions. Then you have Protocol 1, which is called channel streaming. This is the actual engine that allows the continuous streaming of those log data channels. Let's take a look at how these protocols work together in the field. Section 5, Real-World Data Flow, from Sensor to Aggregator. Let's map these abstract protocols onto a tangible rig operation. Imagine a simple streamer connection being initiated by an aggregator. Here's the exact progressive sequence. Step 1. An ETP WebSocket server has to be provided at a known URL. Step 2. That WebSocket is opened using a standard HTTP call. Step 3. A request session message is sent over, specifically asking to use Protocol 1 for channel streaming. And finally, Step 4. Open session and start messages are sent. Boom! At this point, the digital pipeline is officially open and ready for data. But hold on, before raw data can just flow, the system needs some context. The producer sends channel metadata messages. The aggregator absolutely must decode this metadata because it contains the local identifiers for the channels. It takes that metadata and assigns the upcoming stream to the correct, wellbore and log hierarchy. This decoding step is absolutely crucial. It must be completed before any actual log values can be received. If you skipped this, you'd literally just have random numbers with no idea what depth or tool they belong to. Once that metadata is mapped, the real magic happens. The producer begins a continuous sending loop, firing off instantaneous channel data messages the exact millisecond the sensor records them. The aggregator receives them, decodes them, and appends them right to the log object. There is no polling, no waiting. It is just a pure, continuous flow of real-time insight. And hey, when the drilling operation is finally done, Protocol 0 is used once again to send a closed session command and cleanly terminate the whole transfer. So let's summarize the architecture you should really be aiming for here. Both systems beautifully coexist. You keep the legacy WMLS add to store and get from store SOAP functions for your static, non-growing data, things like well headers or survey configurations. But for your systematically growing real-time logs, ETP completely replaces polling. ETP uses WebSockets and JSON to deliver the ultra-low latency that modern drilling absolutely demands. Just remember, successful ETP mapping requires proper prior communication between the producer and consumer to define those channel URIs. Which leaves us with one final thought. Now that you understand the sheer speed and efficiency of the Energistics Transfer Protocol compared to traditional polling, how are you going to implement ETP streaming to completely eliminate latency in your well data architecture? It's time to review the Witsml and ETP specifications, upgrade those systems, and get your data exactly when you need it, right now. Thanks so much for joining me on this explainer, and keep innovating.